Okay, so welcome everyone. It's my pleasure to introduce you Dr. Henri Boffin. I'm going to give a brief talk about his CV. Dr. Boffin is a full astronomer at ESO, working mainly in the user support department, where he supports several instruments. He's also the instrument scientist of the ETC 2.0 for LaCie and parallel instruments, and is also the operation scientist of the Force App project. Previous to his current position at ESO, he was ESO parallel staff astronomer and also ESO's press officer at Garhi. He obtained his PhD from the University Libre de Brussels in Belgium in 1993. And he has also a master in journalism from the École Supérieure de Journalisme de Lille in France. His research is mainly devoted to the world of close binary stars, their formation and evolution, both from observationally and theoretically. And in general, he's interested in all interacting binary stars. He also studies young and older clusters, including finding long tidal tails or looking at the blue star populations. His talk today is going to be about that topic. And finally, he also works on exoplanets, particularly on transmission spectroscopy. I have to say that he's visiting us in the framework of the Fundación Jesús Serra program. Last week, he was one of the lecturers on the summer school Eclipsing Binaries and Astroseismology, which was held in La Palma in collaboration with Dr. David Jones. And right now is giving a short course at the IAC in the afternoons on scientific writing. If you are interested in having a chat with Henri, he's going to be until tomorrow at Matt Huerta's office in the third corridor of the research area. So, Henri, go ahead.
Okay, thank you very much for the nice introduction, and hello everybody. So I'm going to give you a tale of caution about tidal tails, and this is work that I've been doing with Teresa, Giacomo, and Long. So this is a beautiful picture of our Milky Way, which is obtained with the Gaia satellite. And so you can see OM precipities now with all those stars. And indeed, there are some basic questions that we want to really ask ourselves is, I mean, where and how do stars form? And in particular, we would also want to know where and how did the sun form? And what we know is that likely many of the stars, they form in fact in cluster or associations. So how do they populate the galaxy going from those clusters and then finally dissolve into the galaxy? So this is the kind of questions that we would like to answer. And so here I'm going to focus on one kind of cluster, which are open clusters. This is a beautiful example of such a cluster, NGC265. So you can see that this is clearly a nice assembly of stars. And open clusters are gravitationally bound. They contain several hundreds of stars, so much less than a globular cluster, for example. They have a radius of a few parsec, and they get disrupted within 1 to 10 gigayear. So the question that we want to know is how do they get disrupted? And how do those stars, which were in the cluster, finally populate the galaxy? So first, the question is, how do we find the members of a stellar cluster? Well, the answer is astrometry. So this means we are measuring the position, but also this means then the motion and the distance of the stars. And this is something that astronomers have been doing since thousands of years. Right. So the first example was by Hipparchus So in 150 before the current era, he had a catalogue of about 850 stars with a precision of 1 degree. Then later, Tycho Brahe had a catalogue of 1,000 stars, but this time with a precision of 1 arc-minute. A little bit later, John Flamsteed was the first to use a telescope in order to measure precisely the position of stars. And then by 1800, Jérôme Lalande had a catalogue of 50,000 stars with a 3-arc-second precision. And of course, since then, things have improved much more. And a little bit after the catalogue from Jérôme Lalande, Friedrich Bessel, in fact, was the first to measure the parallax of a star, which means the change in position of a star as the Earth goes around, orbit around the sun. And from that, you can then determine the distance to the star. And of course, since then, this technique has been improved and improved, and we have got higher precision on measuring the parallaxes of stars. And what has really made the revolution in the field is the Gaia satellite from ESA. It was launched in December 2013. It is currently at the L2 point, and it has a nominal 5 years mission, which has now been extended for 3 years, and I think they hope to have a further extension of another 2 years. And Gaia has really completely revolutionized our understanding of the Milky Way because it had provided a lot of data. So this is what was done in the early data release 2 years ago, but the data release 3, which was in June this year, did not change much of that, but simply added some more information like radial velocities or spectroscopy and so on. So, but Gaia then provided position for 1.8 billion stars, the color for 1.5 billion stars, and the parallax and proper motion for another 1.5 billion stars. So this is, of course, really completely changing the way we can understand the Milky Way, because now we have such a precision on position of stars and on their distance and how they move that we can really try to understand how they are making up the Milky Way. And in particular, thanks to Gaia, we have been finding many more open clusters. So this is a plot from Castro-Girard et al. And they have found several hundreds of new open clusters. Every new Gaia release, there were basically several hundreds of open clusters that were discovered. And so these allow, of course, to make much more precise studies of all those clusters and how they are linked to the Milky Way. So, but the question we need to ask ourselves is, how can we find the member of a stellar cluster? Because you have all those stars in the Gaia catalogue, but how can we say, okay, those stars belong to a cluster? So let's look at an example. This is another nice open cluster, Melot 66, which is rather far away. It's at 5 kiloparsec. But still, you can see there is indeed clearly some association of stars there. So now let's try to see if Gaia can indeed find all the members of this cluster. So first, what we start to do is that we select all the stars from the Gaia catalogue, which are in a region 1 degree around this cluster. And we can then plot their position in right ascension and declination. We can plot the proper motion, and we can plot the distribution of the parallax. And so you can clearly already see by eye that there is clearly indeed a cluster there. But now, of course, what we want to do is to be able to isolate it. And in order to do that, we are using machine learning methods. So what we are using is a clustering algorithm. And in this case, we are using dbScan. And we do a clustering in a 5-dimensional space. So in both right ascension declination proper motion in both dimension as well as in parallax. And if you do that, then you can now isolate the cluster. And this is the outcome. So you can see that you very well isolate the cluster, both in right ascension declination, but also in parallax, in proportion and in parallax. And this is a zoomed in region, so you can see the distribution around about 5 kiloparsec. So this is why Gaia has been able to revolutionize completely the study of clusters, because we can really now find many members of clusters. And of course, we have also the color coming from Gaia, so we can also make a color magnitude diagram. So this is the one that is shown for the whole region. So it's of course quite messy, but again, if you isolate, then you find very nice single population there with even the possibility of blue structure there. But again, this is a very distant cluster, so the precision is not as good. And if you do the same thing for closer cluster, then in fact you obtain a really beautiful color magnitude diagrams. So the question then is, how does an open cluster dissolve into a galaxy, into the Milky Way? And this is a little movie that shows, in fact, a simulation where you see this is the orbit of a cluster in the Milky Way in galactic coordinates. So this is the X, Y, and this is the XZ, so above the galactic plane. And this is the cluster itself, composed of its star. And you can see that as it is going around the Milky Way, the tidal force of the Milky Way is going to stretch this cluster and creating these huge tidal tails. And the tidal tails will, of course, become more and more bigger. And so all those stars here are simply going to dissolve into the Milky Way. And so all the stellar cluster are slowly evaporating and becoming part of the galactic field, in fact. So, and it is the galactic tidal force that is shaping those stars into tidal tails, which follow initially the orbit of the cluster. So the whole life of a stellar cluster is really written in its tails. And it also tells us, in fact, something about the gravitational potential of the Milky Way, because this is really what is decided the shape and the direction of those tails. So tidal tails of open clusters since Gaia have been then studied by many people. So this is a list of a few of them. I stopped, in fact, the list last year because there were so many to put on the slide. But you can see many people are looking for the tails around cluster because we really want to understand how do the stars populate the Milky Way. And they were all done thanks to Gaia. Okay? But looking at those results, we were wondering if we can do something slightly better and find even bigger tails. And this is indeed one result done by Teresa Jarabkova, where we found, in fact, 800 parsecs long tidal tails around the Hyades cluster. So they are shown here with the blue points in galactocentric coordinates. So we could find really huge tails for this cluster Hyades, which was unknown before because it was very difficult to find them before having Gaia. So how do we find the tails? Again, let's look at a very recent example. So this is NGC 752. It's again a very nice open cluster, which is 1.35 giga-year old. It has a solar metallicity, and it is 450 parsec away. And so you can see clearly it looks indeed like an open cluster. The problem is that when you see this kind of image, which are the stars which belong to the cluster, which do not, which are foreground, which are background, and is there any tail around this cluster? So there were already some work done in 2021 by Agarwal et al. And Wu et al., who detected some tidal tails, but very small ones around this cluster. So it clearly showed that, okay, this is an interesting cluster to study. And also then Bhattacharya et al., again, 2021, they then decided to use the Gaia EDS3 catalog to also look for tails. And what they did is that they looked at a region of 5 degrees around the center of the cluster. And they used machine learning technique again, but using proper motion and parallax. And this is what they obtained. And so they can indeed, so this is all what they consider to be probable member of the cluster and of the tails, with the probability being given by the color. So if it is orange, it is a high probability. If it is black, it has a very low probability to be a member. Okay. So but if you look at the orange ones, you can see that indeed there is the cluster itself, and there is some elongated structure here. And so they found in total 282 members, and the tidal tails extend to 35 parsec on other sides, according to them. But if you remember the results from the Hyades, there we had tails which were covering up to 800 parsecs, so 400 parsecs on each side. So clearly this is less than 1/10 of the Hyades. So is this really the full story? Is it really that in this cluster, the tails are so small compared to the Hyades? So we decided then to look for a much wider region around the cluster to see whether we can or not find such bigger tails. And so the problem is that once you are looking at very extended structures, doing like all the previous works, and including Bhattacharya, working in the just using the proper motion space will not work anymore. And the reason for that is that if you have stars like here, so you have, for example, the central of cluster, all the stars in the cluster, and then you have some other stars which are much further away, and they have all a common proper motion with this cluster. So clearly they came from the same object. But if they are far away on the sky, when you look at them in ERA and DEC, they will be very separated. So if you try to use clustering algorithm in ERA and DEC, may not work. And also in proper motion, they will now be very distinct from each other because of simply the way they look. And if you now look also at the proper motion velocities, then again, they will be very different from each other. And applying a clustering algorithm will not allow you, on those variables, will not allow you to detect them. And that's the reason why many of the previous work did not find the long tails, because they were working in those parameter space here. And so, of course, they can only see, they can do a clustering, and they will find all the stars which are in a very narrow region in this plane. But they will not be able then to catch those objects. And so in order to catch them, you have to use, in fact, what is called the convergent point method, which is a very old method, initially from 1916. This is simply based on the fact that because of projection effects, if you have those three stars and they move all in the same direction, on the projection on the sky, they will look like they all go towards one single point on the sphere. And this is called the convergent point. So they will all look like they go towards this direction. And so if you identify this convergent point, we can then try to, in fact, find those stars. And this is simply done by, if now you have your object and it's moving with a given proper motion here, and you have your convergent point, then you simply draw the circle on the sphere of the sky, and you project the proper motion into a parallel component and into a perpendicular component on this motion. And if indeed it is moving together, then in fact it should move along this big circle, which means that all the proper motion should be in the parallel component. So in principle, if this is indeed one object which is moving together with the cluster, the parallel component should be the full component and the perpendicular one should be 0. And so that's why we can now work in different components, which are in fact the convergent point components, which is the difference between this predicted parallel proper motion minus the observed one, and in the perpendicular we use this one. And so we can see that because of the definition of those two new variables should in fact cluster around 0, 0. If they are moving together with the cluster, this should be 0 and this should be 0. So they should cluster very close to 0, 0. So now we can reapply a clustering algorithm in this variable, and in addition to position and the parallax. And then we can try to use this method in order to find objects which are indeed related to the cluster, much, much farther away. And so we apply this to NGC 752. And what we have to do, of course, is to take Gaia data, but instead of the 5 degrees of Bhattacharya et al., we took a much larger region, a circular region of 24 degrees, which is about 200 parsecs at the distance of this cluster. And this means that we had initially 4 million stars. And then we apply, again, this machine learning technique, DB-scan in the 5 dimension, but using now as the variable the convergent point velocities. And we found, in fact, 640 stars, which are found in the cluster and the tails. And so this is just for fun. I put a circle in red around all the stars, which are indeed member of the cluster. So you can see that it's really not obvious to know that this one is a member, but this one is not. So it's very impressive, the information that you get, because once you get these proper motions and parallax. And so this is now what we then get from those 640 stars. And so if we look now in right ascension declination, well, we can see the cluster very well, and we can see that the tails and they extend over 300 parsecs. The background that is shown here is in fact one of the numerical models that I've shown you initially. And so this is also to make sure that indeed the orientation of the tidal tail is exactly what you expect, given the tidal force of the Milky Way. So the numerical simulation tell us that indeed this cluster, the tail should be elongated like that. And you can see that what we found using the convergent point method and the clustering algorithm, we find exactly stars which are indeed in that direction. You can see here in proper motion, you can see that if you apply the normal technique where you would do clustering, you would only get, in fact, this central region here. But you are going to miss all those stars and all those stars. And while this is not the new convergent velocities, and you can see that we are doing indeed, we are much more compact in this region. And this is the final color magnitude diagram for all the objects. So in orange are the member from the cluster itself, and in blue are the members from the tail. And you can see that they basically all agree very well with the same isotone. So we are confident that indeed we do find stars that do come originate from this cluster and form those tidal tails. And so if we compare now with the result from Bhattacharya et al., the stars in colors, this is what they found, and this is the extent of what we found. Okay, so we find the extension which is 4 times wider than what they found, and we find more than twice the number of stars that they have. Which of course has a big impact also when you try to understand what is the extent of those tails, what is also the total mass of the cluster, what is the initial mass of the cluster, and so on. And this is now again the same plot in right ascension declination, but I have now put here the velocity of those stars. And so you can see that indeed, because of the tidal force, stars here are moving away from the cluster in that direction, and stars here are moving, in fact, in that direction, again, away from the cluster. And this is why, of course, this is going to stretch and make those tidal tails. And this is then the proper motion. And you can see that if you look at the proper motion, but in velocity, we have a spread of about 2 kilometers per second. And if you remember that 1 kilometer per second over 1 mega year corresponds to 1 parsec, then if we look at the spread here of 2 kilometers per second, and we know that the stretch, the extent here is about 150 parsec. So this corresponds to stars which have been ejected up to 75 million years ago. What is also interesting is that the tails are asymmetric. The cluster here you can see is moving in that direction with the arrow in pink. And this is the leading arm and this is the trailing arm. And you can see that in fact, the number of stars in the leading arm are bigger, larger than the number of stars which are in the trailing arm. And this is something that was seen also in the Hyades. Again, you have to look at the blue points. In this case, now the cluster is going in that direction here. And you can see again that the leading arm here has many more stars than the trailing arm. And this is something that is not at all predicted by nominal models. If you put in a potential of a Milky Way, which is axisymmetric, you would not have this. So this is likely telling us something about the cluster initial rotation, or maybe the interaction with some big lump, maybe some gigantic molecular clouds, or it could also tell us something about, in fact, the gravitational potential of the Milky Way, maybe giving us some hint for the existence of Mond gravity, modified gravity instead of Newtonian gravity. So this is also why those are very interesting, because by looking in detail at this asymmetry, we might be able to constrain more the potential of the Milky Way. So Bhattacharya et al., then when they had selected all their members in their tail, they of course then put that into a color-magnitude diagram with an hygroscope, and from that, comparing with the model, you can then also associate a mass to each of the stars. And even so here, I mean, you can see that the match is not excellent. So I guess we have to take that with a pinch of salt, but still, I mean, the method is easy. In principle, you take the closest star from, I mean, the closest part from the isochrone to your star, and you say, okay, this is the mass of my star. And then you can compute then the total mass of the cluster, but also you can compute what is the distribution of the mass of stars in your cluster. And this is what they obtained. And basically a very flat or even declining function. So this is the mass, the logarithmic mass going up here. This is the log of the number of stars which are in a given bin. And so you can see that, in fact, contrarily to an IMF, where you would expect, of course, more less massive stars than more massive stars, here we have something which is basically flat, or even more massive stars or not. And this is, of course, due to the mass segregation in a cluster. In a cluster, it is well known that the most massive stars are going to sink toward the center of the cluster. And also there is this mass loss of stars through the tidal tails, and the less massive stars are more easy to get ejected. So that's why you expect that indeed the most massive stars will remain bound in your cluster, while the less massive disappear. And that could explain then this thing here. And that also shows you why you need to make sure that you understand those details and you know where they are. Because again, this will tell you something about the initial mass function in the cluster. You cannot use the current mass function because there are too many processes which were already ongoing. And they found a total mass in the stars of 240 solar masses. But as you can see here from their plots, I mean, they have indeed very clearly the main sequence, but they have also here a parallel sequence, which are of course binary stars. And so that's why just looking at this plot, it also looks like, well, you should not forget about binaries. And you have to make sure that you take into account that a non-negligible fraction of the stars in this cluster will be in fact binaries. So instead of having one star, you have two stars. And so the less massive stars will likely be hidden into those binary systems. You will not see them because they are in a binary system with a brighter component. So you don't see that they're there, but they are there. They're a member of the binary. And so you need to take that into account, and you need to try to make sure that you also count the low mass stars which are in binary systems. And so this is not the same color magnitude plot for the members that we found, both for the cluster and the tails. And in this case here, I've color coded them according to their masses. Okay, so you can see this is the red giants with 1.74 solar masses, and then going near 1 solar mass and so on. And this is now, again, the tails and the center of the cluster. And here the color is again giving you the same information about the mass. So you can see easily where the most massive stars. And if you zoom in onto the cluster, you can see that indeed most massive stars are inside the cluster. This is where really you can see all the blue and red stars, all the red giants, they are here. There are just a few here as well, but mostly the tails are composed of low mass stars. So that's a direct visualization also of this mass segregation. But again, when you want to then really take into account the mass and look at the mass distribution, you need to include binaries. Okay? And this is what we have done. So we have done a probabilistic approach. Instead of saying that when we have a star here, we don't simply say that we take the closest point to the isochrone and say this is a mass. No, we try to say, okay, is this star here? It could be either a lower mass star here, but in an equal mass binary. And so that's why it increased in luminosity and goes up. Or it would be, in fact, a more massive star with a low mass companion. And that's why it becomes redder. And so you can then make a statistical analysis and try to then say, okay, what is the average mass of this binary? What would be, and of the two components in this binary? And this is what we then used now to look at the distribution. And you can see here the same plot as Bhattacharya et al. So indeed, if we look at all the stars, so in blue is for the primary mass, but in orange is in fact the distribution from the secondary mass, which are in the binary system. And so you can see that this is going then to increase the relative fraction of low mass stars in our cluster. And so instead of having something which is flat or decreasing, it still goes up here a little bit. And this is for the cluster itself. So again, if you look only at the primary, then it goes down a lot. But if you take into account the binaries, then it will go up again. But we still see clearly the effect of mass segregation with many more massive stars which are in. And then this is also then the mass ratio distribution that we find both in all cluster and tails, and this is in the cluster itself. So you can see that the mass ratio distribution, in fact, increase for low mass ratio. So we have indeed a lot of low mass stars which are potentially hidden inside those binary systems. So we can also now go back to our simulation, which was done especially for this cluster. And so we started with a cluster of 5,000 solar masses. And after 1.775 giga, which is the age of the cluster, we are left with about 2,800 solar masses because many of the stars have already evolved. So they became compact objects. And we have 640 solar mass in the central cluster. But what we can see is that in the simulation, the tails will now extend, in fact, much more. I mean, they could extend to over several kiloparsec in the simulation, at least. So, and this we were not able to find them by using our clustering algorithm because we only found an extension of 300 parsec. So we can now do the exercise to say, okay, because we know what the simulation predicts, both in right ascension declination, but also in the galactic longitude and latitude, and in the proper motion, and in the convergent velocity, where again you see those very strange shapes. We can now say, okay, can we then extract from the Gaia data stars which share all those properties? And so this is what we have been looking at. And so now this time we looked at a much more larger region around the cluster. So we look at a region which has a radius of 100 degrees around the cluster. So we had 208 million stars. And we use the models to make some cuts in the various dimensions in order to reduce that to something like 8 million stars. And then we look at all the stars in this catalog, which are close in all the coordinates to the model. And we found in total 1,041 stars that are indeed in close agreement with our model in all the dimensions. And this allows us in principle to retrieve now the full extent of the tail in the cluster. And indeed, we can find that those 1,000 stars, they now extend over several kiloparsec from tip to tip. And so this is how they look like. So now we have here the center of the cluster, and you can see we can then find stars which are much further away. This is again in proper motion, and you can see this very complicated structure, which is what the model predicts. And again, you can see that if you use the standard method, you were only going to pick those stars. No, sorry, those stars in the cluster, very close here. But you are going to miss all that. And here's the same in the convergent point velocities. And this is now the color magnitude diagram. And unfortunately, many of the stars that we pick here, because now they extend so far, so much, many of those stars are in fact faint stars, which are far away. And so the Gaia precision for the moment on the parallax is very poor, which means that the color magnitude diagram is very imprecise. So this should normally be solved with the Gaia DF4, where we'll have much higher precision on the parallax, and hopefully then we can confirm that those huge tails are indeed belonging to the cluster. The other way to do would be, of course, to take spectra of all of those stars and confirm that indeed they share the same radial velocity that we expect from the models, but they have also the same chemical composition as the cluster. So looking now at the masses, we found the total mass with the initial convergent point method. We had a total mass of 536. So about 400 of those are in either primaries or single stars, and 150 solar mass are hidden in secondary stars. And the cluster itself contained 380 solar masses. And when we use this comparison with the model, where we have tails which are much larger, then we have a total mass which now goes up to 800 solar masses. So if you remember our model, we started with a 5,000 solar mass cluster, which then after 1.75 gigayear become a 2,800. So if you compare this value to this value, so it would look like if we did not miss stars, which is a big if, but if we did not miss stars, then you could say, well, then the initial mass of NGC 752 should have been around 2,000 solar masses. The problem with that is that such a cluster does not survive for 1.75. It's too less massive and it will dissolve much too fast into the Milky Way. So this cannot be correct. So in fact, the initial mass of the cluster must be much higher. And this just shows that even by using the other method, we are still missing a lot of the stars from the tails. We have done that also for some other clusters. So you can see here the results for, so this is the one from Teresa, the Hyades in black, but for Coma, Berenice and Prasepe, there again, we can see that we can find very huge tidal tails, which expand even more than the Hyades. When we look also at the number of total stars in the cluster N tails, so for the Hyades, it's 860, Prasepe is more than 1,700. But what is interesting to note is that, again, here for the Hyades, we had this asymmetry, so much more stars in the leading than in the trailing, while for Prasepe, in fact, we have the reverse. And for Coma Berenice, we have the same as for the Hyades, but at a much less smaller level. So there is clearly some asymmetry that we need to explain. So there must be some origin. And that's why in order to try to understand what is the origin of that, we are now in the process in looking at many more clusters in order to find all the tails for all those clusters, and then see if we can relate this asymmetry to some parameter of the clusters. So this is still work in process, so stay tuned. So to conclude, what is the recipe for finding tidal tails? Well, you should make sure that you start with a wide enough area around the cluster. Don't use 1 degree or 5 degrees, use at least 20 degrees or more. Make sure that you are using the convergent point variables into the clustering and not just proper motion, because then you are going to miss the tidal tails. You must be sure that you compare with n-body simulation in order to make sure that whatever you discover is indeed where you expect to find them according to the numerical simulation, and not some other random stars that would just share the proper motion. Use the correct isochrones when you do the comparison so that you have a very good match with your data. And of course, don't forget the binaries when you compute the masses, and especially when you try to compute the mass function to make sure that you don't miss the low mass stars. And this is then the conclusion that the tails of one cluster are much longer than thought, but much more difficult to find. Thank you.
Thank you. Is there any question?
Very nice talk. I'm not an expert on this, but I have some maybe naive question. The first one, you have shown that you are able to compute some model that give you information about what is the expected tidal tail, the complete, in fact, after you look for this kind of star in the Gaia data. My question is, how much the output of this simulation depends on the initial condition? Because I think it depends a lot on where actually the cluster formed, in the galactic plane.
Yeah, no, this is true, but this is why we can also use, in fact, the numerical simulation, and this is what we do. We know the current position of the cluster. We know also its velocity in the Milky Way. So what we do is that we first, in fact, use this as a single point, and we trace it back. So we integrate backwards for the age of the cluster to determine what was the initial position and velocity of the cluster. And this is what then we use as the initial conditions for the
Ah,
cluster.
okay.
And also, I mean, here I showed you only one simulation, but for all the cluster that we do a minimum of 30 simulations, and then we look at the average, in fact, to make sure that we don't. So, in fact, yeah, the results will not change. What will change indeed, maybe, and this is the thing we have not yet looked at, would be to explain this asymmetry. And there, indeed, we need to include then maybe the rotation of the cluster, or we have to change the potential of the Milky Way, or something like that. That we have not done.
The other question was one or two was so related to this asymmetry that you find in some cluster. Could be due to interaction between two clusters.
That could be, of course, but this is, I mean, very unlikely because there are not so many clusters in the Milky Way. I mean, of course, we found many more, but still, there are only a few thousand. So the probability to have really an encounter between clusters is very small. It's more likely that you have an encounter of a cluster with a giant molecular cloud, for example. And so this could be an example. But this is, for example, what we have done for the Hyades, because that could have been an argument to say, well, if there was an encounter with a giant molecular cloud. But then again, because we know exactly what is the orbit of the cluster, we have been looking at, we have traced it back. And if we have tried to see whether there was any giant molecular clouds on the path of the cluster there, and we did not find any. So that's why this is not necessarily the best solution. And that's why one other possibility would be that this is due to modified gravity.
Okay. Thank you.
Okay, so there is a question in the chat, which was also actually my questions, which is, what is the level of completeness on contaminations in your sample for your method that you have with the CP method or using the
Well, the completeness that you never know. I mean, that's a problem, of course. This is what we are in the process to do now. To compute this completeness is, in fact, we are using what is called the, I forgot now the name, but there is some kind of fake Gaia catalog, which has been created by the Gaia people. So they have created a model of the Milky Way with all the stars there, and they have really then put everything like Gaia should see it, and then created the catalog, which is a pseudo Gaia catalog. And we are now in the process of using that and applying your technique to it, and then try to see if indeed how much, because there we know exactly what are the initial conditions. So we know exactly how many stars are somewhere. So we are going to use that in our method and then try to indeed look at how many of the stars are we missing or not, because that's a big question. But for the moment, yeah, we can never be sure that we are complete. And likely we are not, again, because we know that the initial mass of the cluster must be larger than what we found for the moment.
I have a question that in the classification of the star membership of the cluster, why don't we use the UVW component rather than use the projection of the proper motion?
Yeah, this is, I mean, we do use that, in fact, because I did not stress it, but in fact, here you can see, sorry. So this is, in fact, the UV coordinate of our cluster. So when we did the analysis by comparing with the full extent of the tidal phase, we are working, in fact, in the UVW coordinates.
Okay, is that used also in the beginning when you tried to cluster using
No, because the problem also is that if you use the UVW coordinate, then you very quickly become dominated by the error on the parallax. And this is where you will see often that you will have those diagonals in those planes. And so so then in order to be able to use that from the start, you will need to do a cut based on the precision that you have on the parallax, which we don't want to do. We want to be as complete as possible. So that's why we don't do this cut. And that's why then we cannot use directly the UVW plane.
Okay.
Any other question? Something.
I found quite interesting, the fact that once you have recovered the star that belong to the cluster, in detail, you try to obtain the mass distribution of this object. And you have shown the disagreement that there is the theoretical isochron concerning the location of the main sequence. That is a problem related with a shortcoming in the bolometric correction that is used to transfer evolutionary model from the small Russell diagram to the observational one, in the Gaia band in particular. So my suggestion, this is actually my work, is once you have selected the star using the Gaia data, it would be better to make this game using near infrared photometry, because in that plane, isochron match quite well the main sequence. And also you have the additional advantage that the mass luminosity relation in the near infrared is quite less dependent on the metallicity. So you have two advantages with one shot.
Yeah, thank you very much. The problem is that, of course, for most of the stars, we don't have this, because many of those stars are too faint, for example, for 2 mass.
With 2 mass, you don't have this information.
No, that we would have the information only for the most massive one there. So if you go down, it simply doesn't work. So
we are forced to use this.
So that's why we have to try to use some catalogs like Vista, from Vista or something like that. But often we don't find the information. That's the big issue for the problem. So we hope that the theoretician will make better isochron.
So there is no other question. I have another one, which is with your method of the CP method, I can easily conceive that you can find the streams that are for clusters that are not at the upside.
That are not
at the upside. So either at the pericenter or apocenter.
Yeah.
But if you have a stars which is at this apocenter and pericenter, and in your model you don't use exactly the good potential, the differences of energy will lead that the stars will be on completely different orbits, and so you will never find it. So how much are you confident that you can find really the full extent of that, and you are not truncated that close to its upside?
Yeah, that I would not be able to answer that. I have to ask too long with our specialists, but for this, so sorry, cannot. But I mean, again, I've done plenty of tests and I never saw any issue. I mean, the cluster itself is normally enough compact and massive enough that you can follow it as a single point and get the orbit.
For the cluster yet, but the streams is not necessarily following the orbit of the cluster. For example, for M92, one of the globular cluster, which is close to its apocenter, we have a stream which is completely tilted compared to the orbits of the stream.
Yeah, but I think this is mostly also because of that's the big difference between globular cluster and open clusters. I could show this one. Is that in fact open cluster are always very close to the galactic plane. They don't extend so far away, and they don't have very eccentric orbits like globular cluster. So for globular cluster, indeed, it's much more a problem. For open cluster, this is not such a big issue because we are very close to it. I mean, this is also what you saw in yeah. But again, I mean, we are all always very close to the center in the galactic plane. We don't go very far from that. So that's why I think the effect is less. But still, I mean, this is one of the things that indeed we are trying to do by making many simulations for many different clusters. Because there are a few clusters, for example, which have the similar age, similar mass as those ones. And we are unable to detect any tidal tails. So we are trying to understand, okay, is it because it is something real, or is it because indeed it is more like an observational bias? But that we can only do by running many simulation and then checking what we get.
Okay. So if there is no more question, let's thank Henri again for his really nice talk.